So I'd like to talk about our work on ab initio solutions of the many electron Schrodinger equation using deep neural networks. This work was jointly done with David Farr at DeepMind, along with Alex Matthews, also at DeepMind, and my longtime friend and collaborator, Matthew Foltz from Imperial College. There's a link to our archive preprint down at the bottom. Next slide, please. So the electronic structure problem is, I find rich and invigorating, but also extremely frustrating. It's complex, and whilst it seems somewhat academic and kind of obscure, it has kind of profound real-world implications from, and if we could understand it, the electron-electron interaction better, I think it's fair to say we could design better drugs, design better catalysts, understand in the middle how nitrogenase does so much better at fixating nitrogen than the Haber process, for example. And one of my favorite examples of quantum mechanics is that it was shown in 2002 that the reason geckos can walk on walls is due to van der Waals interactions. These incredibly weak short-range interactions, yeah, nevertheless are strong enough to support its weight. And whilst and I want to emphasize these interactions are extremely subtle, and we must be in order to obtain experimentally relevant predictions, we need to be extremely accurate. So whilst the total energy of, say, the nitrogen molecule is around -109 Hartree, the binding energy is only about 0.5% of that. So the total energies can be extremely large, but the accuracy required to obtain predictions relevant to experiment is really extreme. Getting 95% of the way to this total energy is just nowhere near good enough. And in the bottom left corner is easily one of my favorite pictures from quantum mechanics, and it's actually from David Sutherland back in '91, where he showed how complicated the nodal structure, that is, where the wave function goes to zero for an electron gas is. And this talk will show that using a structured neural network, I think will provide a compelling and compact and accurate representation of the many electron wave function, and also that we require second order optimization methods in order to obtain results in a feasible amount of computational time. Next slide, please. So more concretely, we're looking to solve the many electron Schrodinger equation. That is the operation of the electronic kinetic energy with the electron-electron interaction, the electron-nuclear interaction, and finally the nuclear-nuclear interaction for many atomic systems. We're looking to find the wave function for this such that the energy of the system is minimized. And there are a whole plethora of techniques from dating back to the 30s, right from the start of quantum mechanics, and we have, and most methods start from Hartree-Fock, which is mean field approximation, and then we have things like configuration interaction, which is a linear combination of determinants from Hartree-Fock orbitals, the Keppel cluster ansatz, which is substantially more compact than configuration interaction, and we also have quantum Monte Carlo techniques such as variation Monte Carlo, which we will be using today, where you optimize a function stochastically, and then diffusion Monte Carlo, which gives you the exact energy of a wave function of the system, subject to a fixed nodal constraint, normally from a variation Monte Carlo wave function. And there are many, many other methods, but these all start, many of them start at least from Hartree-Fock. And I think the key issue is how do we represent wave functions? Next slide, please. Well, the only thing that a wave function is required to be is it must be anti-symmetric. And this is because electrons are fermions, and there is always a totally symmetric solution to the Schrodinger equation, which is at least as good and normally substantially lower in energy than the anti-symmetric wave function. So if you don't impose anti-symmetry, you will collapse onto a bosonic state that is non-physical. And this is the thing that really makes quantum mechanics for electrons extremely hard. Next slide, please. So the most common and easily the most computationally tractable way of imposing anti-symmetry is simply to represent the wave function as a determinant or a sum of determinants of single particle orbitals. That is, orbitals phi, which only depend upon a single electron at a time. And this wave function that I've written here is actually Hartree-Fock theory, just the best single determinant wave function. Next slide, please. But we can go beyond this. For example, we can include a symmetric term in front of the determinant that just requires to be symmetric, and this can introduce electron-electron correlations. So this is called the Slater-Jastrow wave function. Next slide, please. But nothing requires orbitals to be a function of single electrons. We can have, because we know the wave function is really a many electron object, the key issue is how do we represent these functions? How can we express the function and easily and tractably evaluate it, in particular for the integrals required for things like Hartree-Fock type approaches? How can we represent these single orbitals and evaluate them? Next slide, please. I should say, forgot to mention earlier that with Hartree-Fock and other methods, you express your orbitals on an underlying basis for this reason, to be able to easily evaluate the integrals. And they're typically used, and we typically use Gaussian functions for that reason. So the idea of expressing an orbital in terms of many electrons is not new. It dates back to Feynman in the 50s, and really pioneering work by Davis Eppley and many others from the 90s onwards, applying it to the electron-electron problem, the many electron problem. And the key insight is that if we take an orbital, which depends upon a single electron position, and instead replace it with a function that depends upon a single electron I and all other electrons, subject to the fact that it must be invariant under the change of any of the other electrons, then if we construct a determinant of these functions, the determinant remains totally antisymmetric, and we can naturally capture many electron interactions directly in the orbital. And this approach is used by backflow functions in variation Monte Carlo and diffusion Monte Carlo in particular. But I guess the key problem now is how do we represent these permutation equivariant functions? And in the Slater-Jastrow backflow functions, we typically use a fixed functional form with a small number, maybe a few thousand parameters, up to a few thousand parameters, and you optimize that. But can we do better than a fixed functional form? Next slide, please. So we, and I'm sure, given the title of this conference, many others here will be exploiting the fact that neural networks are excellent function approximators. And machine learning has had deep and kind of profound impact on almost every field that has entered in the last few years. We've seen a kind of a rapid explosion, not just in terms of the interest, but also in terms of the results achieved from protein folding to understanding glasses, to understanding quantum chemistry. Next slide, please. So one way of starting is thinking just about a single electron. So this is the simplest possible case. You can have a single electron, and we feed it into a neural network. And our neural network here is a multi-layer perceptron, where each layer essentially is composed of a set of matrix multiplications with the inputs and some weights, with a bias term added on, and then fed through an element-wise nonlinear activation function. And then that's passed on to an arbitrary number of these hidden layers until finally we spit out, in this case, a single result at the end of the network, our wave function. Next slide, please. And the power of machine learning is really that it can compactly express functions that are extremely high in dimension. So if we want to go to more than one electron, then we can easily handle this by feeding into the network the positions of each electron at a time, and we just need to spit out, rather than a single orbital, we need to spit out the commensurate number of orbitals with the number of electrons, and then we can pass this into a determinant. And this is essentially Hartree-Fock theory expressed with a neural network. But how can we go beyond this single electron picture? And this is the motivation for FONET. We want to continue the ideas from machine learning of breaking away from fixed functional forms as much as possible and see where it leads us. Next slide, please. So I'm going to spend quite a bit of time on this. So with Ferminet, the key idea is that we start with the electron, say a set of electron coordinates, and we can construct rank 1 features, that is, features that depend only upon a single electron position, such as the distance from the electron and the nucleus, or the vector and the distance. And we can also create rank 2 features, that is, electron-electron vectors and distances. We have a structured network, so we feed rank 1 and rank 2 data into an equivariant, a permutation equivariant block, which I'll discuss more on the next slide. But crucially, it produces, from the rank 1 and rank 2 features, it will produce permutation equivariant functions that are rank 1 only. We then feed the output from the permutation equivariant block into a linear layer, and we repeat for several layers. Here I show you three such layers. And finally, we have a single linear layer which takes the output of the block Ferminet layers, Ferminet blocks, and shapes it into the required number of orbitals. We then evaluate the determinants of these matrices, and the final wave function is a learned linear combination of the determinants. But crucially, in parallel to this one electron information, we also have a 2 electron stream, which is fed through just a standard MLP, and the output of each layer is communicated back into the next permutation equivariant block. And we find that this has a substantial impact on the accuracy of the wave function, as we'll show later. Next slide, please. So in the permutation equivariant block, we take the series of rank 1 features, that is, things that initially only depend upon a single electron, and we combine them in a way that's permutationally equivariant. And the easiest way to do this is to take the sum or mean of all of these terms. But we can also do the same with the rank 2 information. So we can take, we go from rank 1, we go from n such information to rank 0 information, and for the rank 2, we go from n squared to order n inputs by combining them in a permutationally equivariant way. We then take the permutation equivariant functions and we concatenate them with the corresponding initial input of rank 1 activations, as shown on the right-hand side. And we then each row of the outputs of the permutation, the equivariant block, is related to essentially a single electron, but depends itself on all other electrons in a permutation equivariant way, which is exactly what we want to, in order to achieve a compact and expressive wave function. Next slide, please. So we can then take the wave function and we can optimize it by minimizing the energy of the wave function. And we do this using standard variation Monte Carlo, where we sample configurations from the net according to the output of the network, the square of the output of the network. We then evaluate the wave function's energy and the gradient of the energy with respect to the parameters, and we use this to minimize the wave function with respect to the energy. There are a few technical issues with this. One is that if we can't just randomly initialize the weights in the network, because this tends to be extremely far from the ground state solution, and is also likely to have linear dependencies in the layers, which causes the determinants to blow up and be singular. So we circumvent this through pre-training of the network against Hartree-Fock in a minimal basis set. But after the pre-training is done, we no longer require any information from Hartree-Fock. And we deliberately do a fairly bad job at this pre-training in order to make sure that the network starts off in a relatively noisy position, so we don't get stuck in a local minimum. And also, importantly, we take very great care over the gradients of the determinants. So even if a determinant is singular, its derivative can still be well defined, and we were very careful to implement it, and found it was incredibly important to implement this carefully in order to obtain obtain convergence rather than hitting nans. And finally, we observe fairly slow convergence of the optimization, and we find that it's crucial to use second-order optimization methods. Next slide, please. So in particular, we use Kronecker-factored approximate curvature, the KFAC method, which is an approximate second-order method designed for neural networks that exploits information about the network and its structure to have a block diagonal approximation to the Fisher matrix, which is computationally much more efficient to invert and also much more compact to store in a sparse matrix representation. And it's essentially an approximation to natural gradient descent and stochastic reconfiguration. And we observe, compared to Adam, which is a first-order optimization method, that KFAC requires an order of magnitude, at least fewer iterations. And we see this on all but the smallest systems, and the gap seems to increase with system size. So here I show the convergence for lithium through to neon atoms relative to essentially exact results from Chakravorty et al. In '93. And throughout this talk, I'll use this gray region to indicate chemical accuracy relative to baseline, where chemical accuracy is 1.6 millihartry. Next slide, please. So let's start by comparing FermiNet against conventional Monte Carlo results on and here we'll just use a single determinant for carbon, nitrogen, oxygen, fluorine, and neon. And this is from really exceptional work by Priyanka Seth et al. Back in 2011. But the results I think are still kind of really, really exceptional. They did a very careful job of the optimization. And they showed that at the VMC level with a single determinant, the Slater-Jastrow wave function is between 2 and 3 millihartries high, but incorporating backflow reduces this by over a factor of 2. Next slide, please. So first we implemented a neural network equivalent of the Slater-Jastrow and Slater-Jastrow backflow functions, and in both cases we see that this provides a slightly but non-negligible lowering in the energy. And this is likely due to the neural networks offering a much more flexible functional form. And I found this slightly surprising because Seth et al. Used numerical hydrophilic orbitals, so they did not have they're already at the basis set. Next slide, please. And then in yellow at the bottom, we have FermiNet, and we show that this shows that FermiNet substantially reduces the error further, well beyond what a Slater-Jastrow backflow architecture can achieve. Next slide, please. And we can further increase the accuracy by outputting not just one determinant, but a series of determinants from the network, and then combine them in a linear combination to produce the final wave function. And we find that 16 determinants is a wonderful trade-off between accuracy and computational cost. So here we show the energy of the ground state energy for a series of atoms from lithium through to neon. And in all cases, we substantially outperform conventional variation Monte Carlo with the Slater-Jastrow backflow function in yellow. And this is now using, the VMC wave functions are now using 50 to 100 configuration state functions, which depending upon the system maps to between 170 and 4,500 determinants. So they're using substantially more determinants than us. Interestingly enough, we also perform at equivalent or outperform the accuracy of diffusion Monte Carlo on top of the VMC wave function. Also shown is the couple cluster with single and double excitations at the complete base, extrapolated to the complete basis set limit, which we substantially outperform, and we also are essentially equivalent to or the CCSD with perturbative triples correction. Also at the complete basis set limit, and note here that unlike VMC and DMC, CCSD and CCSD parentheses T are not variation. And across throughout this, we consistently capture at least 99.7% of the correlation energy, which I think is really, really impressive result. Next slide, please. We've also studied a range of molecules. So ranging from lithium hydride with 4 electrons up to bicyclobutane with 30 electrons. And whilst we see some actual degradation with the number of electrons, this could be for many reasons, problems with the optimization, improvements that are required to the Monte Carlo algorithm, but also we have a fixed network configuration for all these calculations. So the number of parameters we have available does not increase substantially with system size. So for comparison, the bicyclobutane calculation, we have around 700,000 parameters, whereas the couple cluster quadruple zeta calculation has over 22.5 million parameters. Okay, next slide, please. So I'm aware I'm running so short. So we also looked at the wave function itself, and whilst not very much is known analytically, one thing that is known is the behavior of the wave function at where 2 electrons coincide or where the electron and nucleus coincide, and we show this for the helium atom here. And this must be non-smooth in order to cancel out the singularities in the Hamiltonian due to the 1/r potential. And we see the characteristic sharp features at the origin in the top plot for the electron-nuclear cusp, and also below at 0 angle for the electron-electron cusp. We've evaluated the relationship between the gradient of the wave function and the weight value of the wave function of both cusps. And for the electron-nuclear cusp, we find the constant proportionality to be minus 1.99, and for the electron-electron cusp to be 0.493, which is an excellent agreement with the analytic values of minus 2.5 respectively. Next slide, please.
So James, you might have like 5 minutes.
Okay, thank you. So here we show, we study the impact of changing the features to the network fed into the network for the oxygen atom. And interestingly, we find that we absolutely require the electron atom distances for stable training. This is likely due to requiring it in order to model the electron nuclear cusp accurately, at least in the initial stages of training. We also find that the electron-electron interactions are really important. So without them at all, our error is around 90 millihartree, yet with both the electron vector and the electron-electron distance, the error drops by 2 orders of magnitude to 0.8 hartree. Next slide, please. And this shows the convergence of not just Ferminet, but also Slater-Jastrow network, the Slater-Jastrow network and the Slater-Jastrow backflow network with number of determinants. And we find that Ferminet converges extremely rapidly and there's with number of determinants. And this is relative to CCST parentheses T at the complete basis set limit. And we don't see substantial improvements beyond 32 and not really much improvement after 16. And I'd just like to mention that Ferminet is substantially easier to optimize in our experience than the Slater-Jastrow backflow, our Slater-Jastrow backflow network. The Ferminet net calculation we just ran one of, and the Slater-Jastrow backflow network took substantial more work to get stable convergence. Next slide, please. We also studied for H10, and here we use this wonderful study from Motta et al. In PRX from 2017 as reference. The convergence for H10, where each hydrogen atom is separated by 2 Bohr, and we study the energy with both the number of layers, the width of the 1 electron stream, and the width of the 2 electron stream. With number of layers, we see a fairly rapid convergence. We also see interestingly enough, we also see a very rapid convergence in the 2 electron stream, which surprised me. I thought we really would need to capture these very accurately. The key difference appears to be we just need some 2 electron information. But once you have some, you don't really need very much more. I think a more promising avenue is expanding the width of the 1 electron stream, the number of hidden units in that stream, where even by 256 hidden units, which has been our conventional setup for all the calculations I've shown, we clearly still have not saturated the performance of the network. Next slide, please. So there's been a kind of a really wonderful explosion of interest in this topic over the last few years, and I'm really looking forward to hearing about much of this work from the authors of it over the course of this meeting. But I'd just like to highlight kind of some of the really remarkable work. So Luo and Clark used a neural network backflow model to study the Hubbard model. They parameterized the backflow function with a neural network using a first order optimization method, either RMS prop or a custom net optimization method, somewhat related to rprop. And they demonstrated that it substantially surpasses the conventional backflow function for the Hubbard model, which is a lattice system, and the extension to molecules and continuum, I think, is non-trivial. And shortly after our paper hit arXiv, there was work from the NOAA group called PauliNet, where they also looked at molecules and continuum. They parameterized adjuster and backflow functions, optimizing using Adam. So they have fewer parameters than others. It's likely to be much easier to optimize. The energies are, for the boron, they obtain 97.3% of correlation energy, and for the hydrogen chain of 10 atoms, they obtain a correlation energy between 90 and 98%, where the performance degrades as you stretch the molecule. NQS from Kaleo et al. I thought was really wonderful and had a very novel approach where they mapped the many fermion problem to a spin problem, and then so they work in a second quantized space. So they require an underlying basis set, and then they solve it using a restricted Boltzmann machine and stochastic reconfiguration. And they obtain sub-millihartree error compared to full configuration interaction, albeit in a minimal basis. And the error, for example, on nitrogen in this space, the nitrogen dimer in this basis set compared to the complete basis limit is substantial. It's around 2 Hartree. And finally, our work, we also work on molecules in the continuum. We parameterize basically everything at some computational overhead for sure, and we use an approximate but scalable second order quantized optimization method, KFAC, and we obtain for boron a correlation energy of 99.8% of correlation energy, and over 98.5% the correlation energy across the H10 binding curve. And I'd just like to highlight a really neat paper from Ruggieri et al., which studied iterative neural network backflows and applied it to the case of triplet helium liquid. Next slide, please. So just to conclude, FermiNet is a structural neural network for quantum wave functions. We use a powerful, scalable optimization method, and I hope I've convinced you that we have accurate ground state energies with only physically motivated inputs, and neural networks provide flexible and compact representations of complex high-dimensional functions. But I think there's still plenty to do, and I'll leave kind of the list of outstanding questions I think we have for you to read. Thank you very much for your attention.